Hello, in today's lecture, we are going to study Legendre's polynomial. Okay, and as we go on and studying different other topics in physics, like one of them as a follow-up, I'm going to teach is multiple expansion, and also many other places. And also, you've seen the solution for the Laplace's equation in spherical polar coordinates. So azimuthal symmetry also requires you to know what are Legendre polynomials, because the solution itself is in the Legendre polynomials. Okay, so this is quite important topic as far as your net exam is concerned, also as far as your physics part is concerned. So in any case, let us start with the topic. So the topic title is Legendre's polynomial. Okay, and mostly it is taught in a regular classroom program under the title called as special functions. Under the title called as special function. So you can take it as one of the class of special functions that we're going to do today. Okay. So what happens is, so we have been solving ordinary differential equation for quite a while now. Okay. And like in case of homogeneous second order linear differential equation, second order differential equations, one of the ways can be to take a solution in form of a convergent series, okay. And if one wants to take a series solution, eventually what happens is there are at times that the solutions like Legendre polynomials, Hermite polynomials, etc. appear. Okay, so what happens is there are methods to solve ordinary differential equation that we've studied in the previous lectures. One of the methods can be to write a series solution form. Okay, we're not going to see this like how to obtain the solution that you may see in your book. I think Afkin and Weber has done it, but overall we'll focus on the solution part. Okay, and the solutions to these equations, or you can say solutions to these such differential equations, may yield Legendre's polynomial, Hermite polynomial, etc. Okay, and why they're called as special? They're called special because they're you can say they're at times referred to as higher transcendental functions also. Special function. Okay, so they're at times called as higher transcendental functions in mathematics. So what are transcendental functions in mathematics? So you know ILATE. If a function is not algebraic in any one of these categories, the function is called as transcendental, and these fall in the category called as higher transcendental functions. Okay, what these special functions, and why they are special? Because of the difference that they have from the conventional, you can say, from the standard functions, you can say standard functions like sines and cosines and all those things. Okay, so in that sense they are special, and to us they're very special because in quite many problems they would occur. For example, hydrogen atom, you can say. So mostly you'll find Legendre's polynomial occurring in like many of the places. So one of the places we've already studied, that is a solution of Laplace's equation in spherical polar coordinates. With azimuthal symmetry. One of the places where we've seen this is this with azimuthal symmetry. Another place that we are going to see it is in hydrogen atom. As we go along in quantum mechanics, we'll see there. And one of the very basic place that where we see in expressing what you can say, expressing conservative potential, or you can say Newtonian potential, wherever applicable. So Newtonian potential, you can say for a conservative vector field, or you can say for a conservative field. Okay, so many places, I mean, there are maybe many places, as much as I can recollect right now. I have written a few of them. There are many places there where you may find it beyond that also, but mostly in Laplacian equation, wherever you have the spherical polar coordinates with azimuthal symmetry, the solution ends up getting into this Legendre's polynomial. Now, the first thing that you need to remember is the differential equation whose one of the convergent solution happens to be the Legendre's polynomial. Okay, so let us first write what is Legendre's differential equation, and lately when I'll teach you sturm Liouville problem, I'll touch upon what are self-adjoint differential equations also. So right now, I'm focusing to much of the basic content. Okay, so what are Legendre's differential equations? The first thing is, what is Legendre's differential equation? So Legendre's differential equation is of the form 1 minus x square, and you have this d2y upon dx2, and then you have minus 2x dy by dx, and plus n into n plus 1 y. We're not going to write the solution for this. This is a very, very, very long derivation. But in general, here I'll assume that n belongs to 1, and lately I'll fix certain conditions on n for which your Legendre's polynomial would exist. So that we'll see later on. Or otherwise, you want to write, one can write it in this form also. One can write this particular differential equation, the Bord differential equation, in this form as well. Okay, so one needs to understand that this particular differential equation, when we try to solve it, we use a power series solution method, Okay, and when we use power series solution, so we assume a power series centered at 0, that is ak and x ki power k. And this is how we assume one of the solutions. And when we solve this particular differential equation, one of the linearly independent solution, one of the linearly independent solution of the above differential equation. I can solve this also, but the point is that this is going to take a lot amount of your time, and eventually you have to remember the result. So that's why I'm not getting into that thing. So one of the linearly independent solution of above differential equation is called Legendre's polynomial. But one of the things that you need to remember, since it is a polynomial, so it cannot take all the real values. It needs to take only values from the positive integral side. So it can only take positive integral side, and these polynomials are at times denoted by p and x. So p and x, n belongs to natural. So one of the solutions of this, there are other solutions which are called as Legendre's polynomial of second kind. Okay, but right now I'm concentrating on one of them that is called as Legendre's polynomial. Okay, and a few of them one should remember, because at times you'll be confronted in problems. You need to know these things, like p2x is 3x square minus 1 upon 2, and p3x is 5x cube minus 3x upon 2. Okay, so these are some of them that one can remember. And I think one should remember, when it comes to physics, one should remember at least Legendre's polynomial up to order 3. Now you'd say that, okay, whatever you say we understand, because see, I have not derived it. Probably I may derive in one of the recorded lectures and may post it. However, the derivation is not that important. The importance lies in the solution. and one has to admit that if this is the differential equation, one of the convergent solutions to this, and one of the solutions which is of the physical significance, happens only if n belongs to natural. And these solutions are called as Legendre's polynomial. And it turns out that all of these solutions are quite important when it comes to following places where we'll be touching upon. So hydrogen atom we'll be touching upon in quantum mechanics and expressing Newtonian potential wherever it's applicable. For example, multiple expansion, the follow-up topic that we want to do. And other such places, one of the topics we've already done, that is spherical polar coordinates, Laplace's equation solution in spherical polar coordinates with azimuthal symmetry, we've already done. So at many such places, you'll find that this particular differential equation pops out. Now this particular solution pops out. Okay, now one would be very inquisitive as to how one can remember these Legendre's polynomial. Answer to this is very specific and very has been done by mathematicians, and one can use one of the formula called as Rodrigues formula. One can use something called as Rodrigues formula in order to generate polynomials. In order to generate polynomials. So in order to generate the Legendre's polynomial, the relevant Rodrigues formula is given by 1 upon n factorial. You can say 2 to the power n factorial, and this is dn upon dxn, and then you have this x square minus 1 raised to power n. So for example, you want to generate p1x. Let's say you want to generate p1x. So what you need to do is just replace these things here. So this is simply d by dx of x square minus 1, and this will give you x instantly, because x square minus 1 when differentiated would give you 2x, and 2 is here, so it will give you x. I hope it is quite clear. Is that clear or not clear?
No, bhaiya.
Okay. Okay. See, one thing is very much clear. Now, another thing that I should write it here. Okay. Another thing that I should write it here is an important thing that is called as generating function. So let me touch upon generating function, and then I'll again come back to this point called as Rodrigues formula. So let us first touch upon the topic called as generating function. Okay, so what are generating functions? Generating function is that if you want to obtain Legendre's polynomial, one of the ways can be to use the Rodrigues formula. Okay, one of the ways can be to use the Rodrigues formula. The another way is to use something called as generating function. The another way is to use something called as generating function. So generating function is what? So generating function is one of those functions which will help you finding the Legendre's polynomial of different order. So this will help you in finding the Legendre's polynomial of different order. Of different order, you can say. So the natural inquiry is how. So the important part is that one needs to remember that there exists a function, I can write g. Don't get confused by the Green's function. This is generating function in general, or you should write, what should I write? Some other function. Chalo, theek hai, samajhna, generating function. Theek hai? So this is your generating function. And generating function is given by 1 over root over 1 minus 2xt plus t square. Okay, and what happens is if this is the generating, if this is a function, if mod t is less than 1, okay, if mod t is less than 1, then if one expands this particular term in a binomial expansion, what one finds is that you get this equivalent to this particular expression. So what is happening? Whatever term is associated with the power of t to the power n is nothing but it is the Legendre's polynomial of order n. So one can indirectly find Legendre's polynomial from this particular thing also. Is that clear?
Yes.
Okay. And see, where you'll find it very immediately, you'll find this particular thing immediately occurring in any of the conservative, any of the potential, any of the Newtonian potential. So I'll write Newtonian potential for conservative field. So Newtonian potential for a conservative field. Newtonian potential for a conservative field. So this is what I'm trying to write. So what happens is, you know that when it comes to inverse square law forces. So in precisely, when it comes to inverse square law forces, for example, you can say electrostatic force, that is k cube on r square, or let's say Newtonian gravitational force, that is g capital M small m upon r square. In any case, if we encounter something called as inverse square law forces, we know that our potential is dependent upon 1 over r. So it is dependent as a function of r as 1 over r, because it is inversely proportional to the distance of the point particle where we want to find the potential. Uh, uh, that is, it is inversely proportional to 1 over r, where r is the distance of the particle in question, or the point in question where we want to find the potential from the source. So this is your source, and this is your r. So if you want to find the potential here, it will be like k upon r. You can take it as kq upon r. Like k means not always that k. There would be some constant divided by r. So it can be minus g capital M small m upon r also. Yeah, अगर यहाँ पे mass दे रखा है, then the potential can be minus gm upon r. That is a gravitational potential. Or otherwise, if it is a charge q and we want to find electrostatic potential, it can be capital kq upon r. In any case, this is constant over divided by small r. So I can say that my potential is inversely proportional to r. Is that clear? Now let us try to derive one of the. Let us try to uh, write the most general case. Okay, so let us suppose we have a mass, or you can say charge, whatsoever suits you. Like if it suits you to write a electrostatic case, then like you can take it can take in the manner of electrostatics, or if you want to take it in a manner of gravitational potential, you can take it in gravitational potential as well. So this is your origin. Let's say this is your, let's say, point P, and let's say this is your point Q, and let us suppose that your mass M is located at some point, let's say here at point P. So let us say that mass M is located at point P. So let us say that your mass M is located at point P, and which is distant at, so you take some distance here. So let us say this distance is a, constant a, and let us say this is your phi. Okay. Okay, and we want to find, and we want to find potential, like any sort of potential, let's say gravitational potential at point Q, at point Q, which is r distance away from P. So let's say this is at r distance away from P. If it is at r distance away from P, and we want to find potential at this particular point. We want to find the potential at this particular point Q. And from the law of cosines, it is quite clear that if you remember the law of cosines, this distance OQ, this particular distance R, and this particular distance OQ. So if let's say this is इसको कुछ ले लेते हैं ना, let's say this is B. So instantly you know that your R square is equal to A square plus B square minus 2AB cosine of phi. So from law of cosines, if you remember, so this is how you can express your R. Is that clear? So by law of cosines, you know that your R square can be expressed in the form of A or B, and take anything, like let's say your here B is greater than A. Let us assume that B is greater than A. Okay, so you have two different sides of different magnitudes. Let's say this is A, this is B, and this is R. And we want to find the potential at Q. Is that clear?
Yes.
Okay. So because of this particular mass, the potential at this particular point would be the like distance, whatever separates them, some minus gm capital and whatever you gm upon r, and I would stick to something like k upon r. So let us take it as a general case. If mass is there, I would be interested in finding gravitational potential. If charge is given, I would be interested in finding electrostatic potential. So let us write that the potential at q, potential function at q would be simply k over r. Is that clear? And since I know that my r is nothing but it is equals to a square plus b square minus 2ab cosine phi, and that also root over. So this is what it is going to be, right? So one can do is one can take the larger one common out, larger one common out. So I'll take a larger one common out. Why I'm taking larger one common out? If A was larger, then I would have taken A common out. If B was larger, I'll take the B common out. Okay. And why I would do that? Because that would reduce my arguments in a way that I can use binomial expansion. So this will form K upon B, and then I'm left with 1 over root over 1 minus, sorry, 1 plus, sorry, 1 plus कर लेते हैं इसको, and that will be A upon B का whole square. And then I have a term called as minus 2a upon b, and then I have a term called as cosine. Is that clear? Okay,
Yes,
is that
sir.
clear? Okay, so what happens is that one can recollect from the Legendre's polynomial that that the generating function of the Legendre polynomial is given by 1 of minus 2xt plus t square, where mod t is less than 1. So instantly you can say that, okay, this t, in place of t you have a cos phi. In place of t you can also take this, like, because I've already told you that b is greater than 1, b is greater than a, so your a over b would be less than 1. Is that clear? So this takes the place of t square, and like in place of x you have cos phi. So if you want to express, I'll write it here. So if you want to express, I want to suggest you that this is what I want to say. 1 plus you have a t square, and then you have minus 2t, and then you have x. Is that clear? And you know that your t is less than 1. Is that clear? So I've already told you that this particular expression serves as the generating function for the Legendre's polynomial. And you can see that, okay, this potential, if I want to express, I can express in this form as well. So I can express in this form, that is n equals to 0 to infinity. And you have p n x instead of p n x, you have p n cos phi. And then you have the term a over b, and then raised to power n. The a is less than b. Is that clear? So any such potential which stands out from a conservative field, and especially for the inverse square law forces, happens to be dependent inversely over r. And what one will find that an execution of r in terms of law of cosines. Okay, so if you want to write r by using law of cosine, it would invoke you eventually to write the expression in terms of the Legendre's polynomial of various orders. So this is one of the places where you'll find most of the times that this particular Legendre's polynomial would occur. Is that clear or not clear? So I'm not getting into mathematical intricacies of deriving things. If you so want, I will do it. I'm not saying I will not do it. I may do it, because if I'll find time, I'll solve all these trees ke beech ke derivation part. I'll solve them up. But I want you people to make most of the hold on this, because that I can because this is what one needs to remember when it comes to physics. Is that clear?
हाँ भैया.
Sir.
Okay. Okay. Another thing that one can see quite significantly is that P naught x, you see it came out as 1. P1 x, it came out as x. P2 x, it came 3x square minus 1. And P3 x, you can see it came out as 5x cube minus 3x upon. So all of these are the different polynomials you can say. And what one can see is, if I replace x by minus x, what I'm getting minus 1 raised to power n p n x. That is, for odd n, it is an odd function, and for even n, it is even function. This instantly you can see from here. Okay, so this is one thing that one needs to remember, and this may you can this is something that you can do also. So, for example, you know that your generating function is given by 1 over root over 1 minus 2xt plus t square, isn't it? And this is equivalent to writing summation pnx t raised to power n. Is that clear? Now replace x by minus x. You replace x by minus x, so your generating function would correspond to root over. So I'll write it as 1 here. And if you replace x by minus x, this will be it. So it will be like 1 plus 2xt plus t square is equal to summation pn minus x and then t raised to power. This is your equation number 2. Is that clear? Okay, so I'll use this thing by saying that, okay, in terms of like here, what you can do, you can place something like you can write it as 1. I'm writing this here. I can write it as minus 2x, and then I can also write it as minus t, because if I want to write plus 2xt, I will write 2x and then I'll write minus t, and then also I'll write t ka square instead. I'll write minus t ka square, and this will give you pn minus x, and this will be t. Instead of t, I have minus t raised to power. Okay, sorry. देखो करना क्या है? For example, if you want to replace this, so I have replaced x by minus x. So if I replace x by minus x, this would be it. And now, sorry, if I want to write it in this form, so instead of t, if I replace t by minus t, these two things are equivalent, isn't it? These two things are equivalent. Like this and this are equivalent, isn't it? And I know if I want to write 1 minus 2xt plus t square, and if I want to write 1 plus 2xt plus t square, what I'll do, instead of this writing minus here, I'll say, I will simply say that this is minus here, this is 2x only here, and instead of t, I have minus t, so this resembles the above structure. But what happens is, here there is no negative in front of x, rather there is a negative in front of t. Is that clear? So this particular thing would reduce to summation pnx and minus 1 raised to power n and then t raised to power n. So this is equation number 2 and this is equation number 3. They're actually the same. We are actually expressing both of these things only. So if I equate both of them, what I'll get? I'll simply get that your pn minus x is nothing but it is equals to minus 1 raised to power n pnx. Is that clear or not clear?
Clear.
Okay. भरत समझ में सिंपली कुछ नहीं करना है, यहाँ जो आपका प्लस 2xt है यहाँ माइनस रहने दो, 2x के 2x रहने दो, instead of t write minus t. One of the ways to express this particular thing is writing in this manner also, no? So eventually this ends up we end up getting this, because here I'm not replacing x by minus x. I'm simply writing that instead of expressing this, I can express this particular expression by saying that I have written minus t in place of t. That will also give me the same expression as on the left hand side of the equation number 2. So equate them up and you will get that pnx is minus 1 raised to power n pnx. So this is quite fundamental, and that is something that you can do from your generating function as well. Okay. Now when it comes to finding pn1, so what you can do, what would be pn1? So pn1 क्या होगा सोचे? So pn1 would be simply writing again use the generating function. This is not summation. This is equal to 1 upon root over. So instead of x, you have 1. So I'll write 1 minus 2t plus t square. Okay. So if I want to use this, so if I want to find pn1, what I'll do, I'll simply replace at x equal to at x I'll replace 1, and this will give me summation pnx t raised to power n from n equal to 0 to infinity. and instead of x you have 1 here. So this is Pn1 t raised to power n. And what is this? I mean, this is what what you can say, that this is 1 minus t raised to power minus 1. See, this is 1 minus t square. You can see this is 1 minus t square clearly. This is 1 minus t square, and this is raised to power 1 by 2. So this is 1 minus t square raised to power 1 upon 2. So this will give you 1 minus t raised to power minus 1. So this is from n equal to 0 to infinity. This is your Pn Pn1, and then you have this t raised to power n. Express this, what you'll get? You'll get 1 plus t square plus t cube, so on and so forth. And there also you can see this is Pn1, 1 plus t square dash dash dash. So eventually, from both of the ends, you can compare and find that your Pn1 in any case would remain equivalent to 1. Sorry, Pn1 in any case would remain equivalent. Is that clear? So two of the properties which are very important, one of them is that Pn, that is the Legendre's polynomial, is an odd function for odd n. The Legendre's polynomial is an even function for an even n. Another property is that at 1, whatsoever may be the n, that is, it may be even or odd, Pn1 would remain as 1. Is that clear? Okay. And another thing that one needs to remember, being from physics background, is that whenever you will encounter some Newtonian potential, at the end of it, if at all, it follows the inverse square law of force, one can express a potential in form of various linear combinations comprising of Legendre's polynomial. So this is one very fundamental result, one of the very fundamental results. And this is something instantly we're going to use in our class in multipole expansion, which is to follow soon. Probably tomorrow I'll take a class, or day after, once I'm done with this. Another thing that I would say, that probably I may record a lecture on at least a solution part of it, but right now I'm not interested in it, because that it demands extreme care and caution, and all these things I'm writing like in a very this is coming out from my memory. So for that I need to sit down and write each and every step, and then only I can dictate all those things. So basically, that is a very long kind of derivation that you can see on my books also, but I'll do anyway for you. But understand the fact that if you are given a differential equation of this form, one of the convergent and a very physically significant formula, a significant function that pops out as a solution for this differential equation is the Legendre's polynomial of various orders. And I've taught you that all these functions you may find at many such places. One of the instances I've given you, one of the instances we've already discussed in quantum mechanics, in electrostatics, and one of the instances we'll see as we go along and do multipole expansion. So one of the examples where generating function would be used is multipole expansion. Okay, so that we are going to do tomorrow, probably day after. Another property that one needs to see is Pn minus 1, what it would be. What do you think it would be? So just try to put this thing in these things. Like for exam, I'm saying, if you remember at least 4 of them, you can instantly write what is minus Pn minus 1. What would be Pn minus 1? What do you think is Pn minus 1? Alpna, what do you think Pn minus 1 would be? So instantly you can see
माइनस बाहर आ जाएगा बस.
Okay, so this will be this, because for odd n, you can see that this is minus 1, and for even n, you can see this is 1. This is something that you can do on your own also, but let us try to do it from the generating function that we've done, right? So let us use generating function, and the generating function is given by 1 minus 2xt plus t square. So instead of x, you have to replace this. So I'll write 2xt, and then I'll write t square is summation p n 1, minus 1 t raised to power. Is that clear? And if you just expand this term, so this is 1 plus t raised to power minus 1, and this is summation pn minus 1 raised, and then you have t raised to power. Try to expand on both ends. This will be minus, this will be t square, this will be minus t cube, this will be t raised to power 4, this is minus t raised to power 5, so on and so forth. And here also you'll find that this is pn minus 1, and instead in this t raised to power n can be written as 1 plus t square plus t cube so on and so forth. And on comparing on both ends, you can see that for odd n, this Pn minus 1 is becoming minus, and for even n, Pn minus 1 is becoming 1. So I'll write Pn minus 1 is nothing but it is equal to minus 1 raised to 1 by comparing from the above expression. Is that clear or not clear?
हाँ भैया.
Okay. So one of the things, one of these these are quite important results, and often you'll find in exam like these questions are straightway coming. Okay. Okay, just give me a minute, and I'll jot down some very important properties for the Legendre's polynomial as I go along. Okay. So I'll do them. I'll do the difficult properties as I go along. But right now, let us focus on. Just give me a minute here. Let us focus on orthogonality property. There's an important topic, a mathematical intricate topic called as recurrence relation that we'll do. But the point is this: in any case, in exam, that will be of no use. However, I'll do it for you. But for exam, you'll need a different skill, and I'll teach you that skill as well. So, what are orthogonality relations? So, orthogonality property. Orthogonality property. So, what happens is we found that these Legendre's polynomial all we know, and lately we'll find that these will form these orthonormal these, and whenever you as we go along in doing vector spaces, we'll find that functions being orthogonal are quite important to us because in any case they can form a basis set for us. Okay, so this is something that we're going to go we're able to see as we go along in quantum mechanics also, and in the treatment of vector spaces. What one finds is that these Legendre's polynomial are orthogonal to each other. What does orthogonal mean? So, for example, if I say that my function fm, and if I say that my function fn are orthogonal on, let's say, an interval a comma b, then what does it imply? It implies this particular integral is equals to Kronecker delta m. And often you may find for other different functions, you have some constant here. You can see them as a weight function. For some functions, you may find x written here. For some functions, you may find x square written over here. So these weight functions may exist. But for Legendre's polynomial, the weight function is 1. And you can say that Legendre's polynomial follow orthogonality relation in the interval -1, 1 given by this. Is equals to 0 if m is not equal to n, and if m is equal to n, then it is equals to 2 upon 2n plus 1. Is that clear? Okay, and one can see where we get this from. So as we know that Legendre's differential equation is given by 1 minus x square y double dash, and then we have minus 2x, and you have y dash plus n into n plus 1 y equal to 0. And if this is the differential equation, one can see that Pmx and Pnx, both of them satisfy this differential equation. And I can write them as d by dx of 1 minus of x squared. And then I can write Pm dash x and minus 2x. And I can write Pm dash. And then I can write n into n plus 1. I can write as Pm equal to 0. And similarly, I can write d by dx of 1 minus x squared Pn dash x, and then I can write minus 2x, I can write Pn dash, then I can write n into n plus 1, and I can write Pn equal to 0. This is your equation number, whatever, this is equation number 1, or you can say 2. Okay, so if I multiply this particular differential equation, 1 by Pn and this by Pm and subtract them, what I will get is, I will get d by dx, and I will write 1 minus x squared, I will write Pm dash Pn minus Pn dash Pm minus, this would be minus, what should I write? Okay, so I should write it as Pn dash Pm dash, right? So I think instantly this will get, acha, ye bacha reh jayega na? This is not n into n plus 1, this will be m into n plus 1. If this is m, this is m, this will be m into n plus 1, this will be m into n plus 1. Okay, and if you see, if I write it in this way, so for example, चलो मैं तुम्हें ढंग से समझा दूं इसको कॉम्पैक्ट करके, because I am having lack of time, so कोई बात नहीं, so एक मिनट रुको बस, so एक काम करते हैं, ढंग से करते हैं, so I'll write it in this way, I'll write it in 1 minus x square, चलो इसको ढंग से लिखते हैं, this is pm, इसको ऐसे नहीं ऐसे करते, चलो कचरा हो गया थोड़ा सा जल्दीबाजी के अंदर, what I'll do is, okay, so just give me a minute. I mean, I'm having only 1 minute left, so I will join another meeting. Hardly for 15 minutes I'm going to take because I don't have much time today. But let us finish this derivation first. So I'll take another lecture. Hardly 15 minutes I have to take, not more than that. Okay, just give me a minute. So I'll send you that link.